Hello, my name is Guilherme Del Fiol. I am faculty in the Department of Biomedical Informatics at the University of Utah. Today we're going to talk about health information standards and interoperability. These are very important topics in healthcare, given that we have information flowing from individual to individual, organizations to organization to support activities such as patient care, research, and public health. Ideally, we should be able to flow information smoothly and without losing any kind of information along the way. Talking about standards, if we look at, we should all love standards. Without standards, a lot of the things that we have in our lives would not be possible. A perfect example is our railroad system that was built in the last century. Without standardizing the size of the railroad and the trains and the train stations, we would never been able to communicate, to have the trains flowing from one coast to the other in the United States. Standards also, the periodic table is another perfect example. I'm sorry if it brings bad memories and nightmares from high school, but the reality is that chemists use the periodic table to communicate, and without this kind of standardization, the scientific discoveries in chemistry would be very difficult to communicate. We have similar examples in math, in biology, in everywhere you look in terms of science, there will be standards to help researchers communicate. In our daily routine, we also have standards all over the place. If I go book a trip on an airline website, you will be able to search for an airport based on the airport code. And those codes are standardized across the board. You can book a flight on Delta, American Airlines, or any international airline company, and the city codes will essentially be the same. Another great example is our lovely ATMs. Back in the day when we didn't have ATMs, we had to stay in line at bank, and that was a nightmare. Um, Even within an ATM, we have several standards. You can see the place where we insert our cards, the size of the card is standardized, the magnetic stripe that's on the back of the card is standardized. The card reader also follows the same standard, so it's able to read any card that you insert in the machine. The keypad, the numeric keypad is pretty much standardized. The numbers are positioned in the same way no matter what ATM you use. And all of them kind of look the same. You have a green button for confirming some kind of action, a red button to cancel, and you should expect to have some kind of place where you can get a receipt of your transactions. So not only you have standards for devices to interoperate, but also user interface standards so that we don't have to relearn how to use an ATM every time we use a different one. Other examples, Kayak, a website for finding travel deals, airline tickets, hotels, cars, uses standards to communicate with the different airline companies, hotels, and so you can search for deals and you can also book uh, your trip with those companies. So Kayak uses standards to communicate with all those different systems, and it also uses standards to communicate with when you buy a book a hotel and have to pay for that transaction. It uses standards for that as well. We also have standards in your own computer. Even when you are not communicating with any other system, you just have, let's say, a standalone computer not connected to the internet, different files on your computer will follow different standards. Adobe PDF, for example, is a widely used standard, document standard, so you can exchange files um, with other people who might be using different systems. MP4, another example of a standard file format for video files. Without these kinds of standards, we would have a nightmare of translations from file format to another file format. And those of you who have tried converting, for example, a Microsoft Word file to WordPerfect, or Microsoft Word to OpenOffice, probably have experienced the kind of losses we have when we try to convert from one standard to another. So that's great. We have standard file formats. Here's another example. This is more recent in how much do we like when we don't have to remember our emails and or our username and password, or have to type them to log into a website. So this is based on a standard called OAuth. It's an authentication standard that allows you to use your credentials from a website like Facebook or Google and use the same credentials to log into other websites. Okay, so we love standards so much that sometimes we overdo them, and they just proliferate, and we end up with several competing standards. So this cartoon gives a great example of how we end up with so many standards. And in healthcare, I think this is particularly problematic. So like we said, standards are really good until you go to a place or you start using a system that uses a different standard that's not compliant with the ones you are using. So you go to Europe, you try to plug in your favorite gadget, and quickly realize that it won't fit into a standard European power plug. Here's another example. We got several standards for cables in devices like USB, and in this example, we just created business for a company that helps you navigate from the multiple cable standards and input devices. So in health information, we have use for standards all over the place. In research, you can think of standards that can help you identify patients for a randomized clinical trial. You need standards if you want to build a registry across organizations, that all these organizations are going to send data to this registry. You need some kind of standard, even if it's a de facto standard that all the different parties agree on. The biomedical literature has standards that allow indexing citations and so to facilitate retrieval of articles. In patient care, we have also standards all over the place. Nowadays, we have the notion of e-prescribing, so clinicians using an EHR to prescribe medications to the patient. In such a system, you have a catalog of medications that are usually coded using some kind of standard. EHR system needs to communicate with a pharmacy so that the prescribed medications can be electronically transmitted. That also requires a standard. Another example is health information exchange. We have different healthcare organizations with different electronic health record systems, and if ideally they would be able to freely and smoothly exchange information to support patient care. And those kinds of activities require standards. So at least two organizations that want to exchange information need to agree to use the same standard. And we have several other examples on the screen. For public health, also for reporting of diseases that need to be notified, for disease surveillance, outbreak notification, All of these activities require some kind of standard, or at least the parties involved need to agree on a common set of standards. I'm going to walk you through a few examples that we mentioned in the previous slide. Um, Perhaps one of the most widely adopted standards for healthcare is standards that support billing. So we have terminology standards such as ICD-9, ICD-10, and also CPT codes for procedures. In the United States, without these terminologies, we would have no billing. Healthcare organizations would not be able to tell what services were provided to the patient to insurance companies so they can pay. In the electronic health record system, we have several applications that could benefit from standards. This screenshot uh, from Intermountain Healthcare shows a list of patients. As I start typing the name of a medication, it looks up a list of medications in a standard catalog that has all the medications available for prescriptions. And behind these items on the screen, we have standard codes that can be communicated to the pharmacy. Here's another example. We got an order set in an electronic health record system. Serves like a checklist for specific conditions. I have a patient with severe community-acquired pneumonia, and this order set helps me remember all the things that could be ordered for this patient in the hospital. Now, there is a standard for the representation of order sets that allows a knowledge company, a publisher, to create knowledge content for order sets and sell those to healthcare organizations. So we don't need the same kind of content, the pneumonia order set, to be recreated by every single healthcare organization. They could buy content or acquire content from the public domain and import the content into their system, very much the same way you download an MP4 or you download uh, um, an audio file to your computer and listen to it. Another example is quality measures. So we have standards that allow the representation of quality measures in a way that can be computed and executed by the computer. In CMS, for example, has a number of quality measures represented in this standard format. Within a quality measure, um, there's a need to represent things like conditions, medications, lab results, assessments. And those representations use standard terminologies such as ICD-9, ICD-10, and SNOMED-CT. So this is an example of all the codes that are included in this hypertension blood pressure measurement. All these different things are relevant for this quality measure. So here's another example with the same idea. The CDC has a list of reportable communicable diseases, and those diseases are represented using standard terminologies. They have a human readable list on the CDC website, but each of those can also be represented in terms of standard codes that can be processed by a computer. So different healthcare organizations can download this standard list and import them into their system for various kinds of applications. Another example of where standards can be useful. Let's say we have a multi-center clinical trial that needs to recruit people from different healthcare organizations, and they want to use the computer to identify those patients. But each healthcare organization might be using a different database, a different EHR system. So we would like to be able to query those patients in those different systems, but using ideally a standard mechanism. So this article talks about a system that implemented criteria for inclusion of patients in a randomized control trial. And as you can see, you have different uh, rules for the inclusion criteria. You need a patient who's above 40 years old and any ICD-9 code for diabetes type 2 and a hemoglobin A1C greater than 7.4. So to be able to find these patients across systems, we need a standard way to query for those patients. Here's another example. Those of you who are familiar with PubMed and you start typing a search on PubMed, in the first place, you get a list of potential search terms. So this is actually looking up a standard terminology called mesh that runs in the backend within PubMed. And PubMed Medline, which is the database underneath PubMed, has all the citations indexed using the mesh terminology. So thanks to this kind of standard, we have the much better ability to search articles within PubMed. If I find an article, let's say this is on myocardial infarction, another way of looking at it is the underlying representation of that article. And as you can see here, highlighted in blue, one of the indices for that article is myocardial infarction. So it is using the mesh term myocardial infarction to index this article. And likewise, we have standard terms for things like this is a diagnosis article, and this article is about mortality. So all the entire citation index uses mesh terms to facilitate information retrieval. Okay, let's talk a little bit about interoperability. Um, the general idea of interoperability is that you have two systems, two information systems, and there's a desire for those two systems to exchange information. So information would go from one system to another and potentially vice versa. And there's a desire when we have interoperability, we should be able to make sure that the information that goes from system A to B remains intact. There's no loss of information. There's no the information that system B expects to receive is all sent by system A, and there's no misunderstanding on that information exchange. So there's no breaking in the information flow. Now let's look at the different components of interoperability. The first one is network connectivity. This is a super simplified diagram, but I think it captures the essence. Number one, you need, for two systems to communicate, they need to see each other on the network. So in drawing a parallel in highways, when a highway is interoperable, it means that it connects to another highway, and cars can flow through that system. In a computer, one example is your computer is connected to the internet, or two servers are connected through the internet and they can see each other on the network. But that's not enough. That just means two computers can see each other. That doesn't mean they can exchange information. So, and they can understand the information that's being exchanged. So the next level is a syntactic interoperability. And one example of that is file formats. So you have things like HTML, PDF, text files, Word documents. So two systems, to be able to communicate, they have to agree upon a standard file format. That's not enough. That only means that I'm able to send you a text file and you should be able to open that text file. It doesn't mean you're going to be able to understand the contents of that text file. So the next level is called semantic interoperability. And in healthcare, this is critical. I want to be able not only to receive a patient's record from another healthcare organization, I want my EHR system to be able to open that record and place the right elements of that record within my EHR. For example, the patient problems, the medications, the lab results. And if my system does not understand those things, you won't be able to process the record. Now, quite often in healthcare, we end up in challenges such as having multiple standards or having lack or suboptimal interoperability, like we have in this cartoon. Uh, there's often a misconception that we can map things from one system to another, and usually mappings are quite challenging, and there's loss of information. And the perfect example is when we map from the ICD-9 code system to ICD-10. So as a result, this is our most widely interoperability device and standard in healthcare. A lot of people still can't believe that we have fax machines in offices and hospitals, but that's still the most common way of exchanging patient information across institutions. Okay, let's talk a little bit about terminologies and information models and their distinction. So, terminologies are collections of concepts and terms. We're going to talk a little more about that, while information models provide the slots for those concepts and terms. Examples of terminologies include ICD-10, SNOMED, RxNorm, LOINC, and information models, standard information models. Examples include HL7 RIM, FHIR, the MIMIC dataset, which is some kind of a de facto standard, same as OMOP. Terminologies are constantly expanding. Every time there's a new diagnosis, a new lab test, a new medication, a new concept needs to be added into a standard terminology. Information models, on the other hand, ideally would be more stable so that information systems can implement those models and not have to change all the time. So let's drill down a little bit into the standard terminology. So I mentioned that it's a collection of terms, and the goal is to convey information unambiguously. And so it's all about semantics. Examples of terminology components include a concept, which is a specific meaning that might be assigned a set of terms, which are basically words or human readable representations of the concept. We might have one or more synonyms of the term, and we might have codes that represent the concept, and also multiple relationships between concepts. So here's an example. We have the concept myocardial infarction, which is represented by this term, myocardial infarction. Can have multiple synonyms. One of them is more consumer friendly, and we have an acronym. We have a code. This is just a number that represents myocardial infarction. Computers like numbers much better than textual representations because they're not ambiguous. So every standard terminology has those codes. A concept can have parents, so myocardial infarction is a myocardial disease and is a structural disorder of heart. And it also has children, so it has hierarchies. One example of a kind of myocardial infarction is acute myocardial infarction of inferior wall. And we also, the anterior wall is another kind. So these structures in standard terminologies help with a number of computer applications, and it help provide interoperability. Concepts also quite often come with some kind of explicit definition. Just to give an example of available and widely used standard terminologies in healthcare, each of them have different coverage. For example, ICD has reasonable coverage for diagnosis and procedures. It has pretty much nothing on lab tests, drugs, assessments, etc. CPT is all about procedures. It's more like a menu of procedures for billing. LOINC is focused on lab tests and assessments, and SNOMED is a more comprehensive terminology that covers various aspects of healthcare in uh, varying degrees of completeness. And RxNorm is completely focused on medications. So as you can see, we have the problem of multiple standards. They're not, they overlap, but they're also complementary. But that imposes a dramatic challenge in terms of achieving interoperability, because information systems might need to be able to handle all these terminologies, which have different structure, different kinds of codes, and synonyms, and the way you use those terminologies is just different. So systems have to be able to handle all of them. So here's an example of how different components in a terminology can be used for different reasons. This is the RxNorm medication terminology. Within RxNorm, we have two main dimensions. We have generic terms as well as brand names. So on the left side, we have generics. On the right side, we have brand names. So here I have diazepam is a generic name for a drug, and Valium is one example of a brand name. So as we go down in the structure of RxNorm, we keep adding more information. So we call this different levels of granularity. Here I only had the name of the main ingredient of the drug, or the name of the brand. There was no information about strength, route, form, and etc. Now, here we have a relationship that tells diazepam 10 milligrams, or diazepam is an ingredient of diazepam 10 milligrams. So here now we added the strength of the drug on both sides. As we go down further, we keep adding more information. Now I have also that this is an oral medication and the form is a tablet. And both drugs have relationships with a form, oral tablet. So each of these levels is useful for specific kinds of applications. If I want to prescribe a drug to a patient, I need the strength, the form, and the route. So this would be the right level for that kind of application. Other kinds of applications, for example, if you want to find patients to recruit for a clinical trial, and all you need is patients who are currently taking diazepam, then the best level for querying those patients would be at this one. But in the EHR, patients would be represented, or the prescriptions would be represented at this level. So there would be a mismatch between what I would like to use. I don't want to have to list all the possible representations of diazepam. That would be a very long list of codes. I just want to be able to say diazepam, anyone on diazepam, any kind of diazepam. So this is where a terminology with explicit relationships could help. You would tell the computer, I want patients on diazepam. The computer would then expand this to all the different forms of diazepam, and behind the scenes query the database with all those options. Okay, another example, LOINC is a terminology for lab tests and assessments. The structure of LOINC is very different than the one I showed for RxNorm. Basically, you have a code that has that format. There's a set of numbers plus a verification digit. We have the main component of the lab test, the analyte, in this case coagulation thrombin induced. We have a property, the timing, so this was done once as opposed to, for example, over 24 hours. This is the system. The scale is a quantitative scale as opposed to ordinal or qualitative. And this is the method used to produce this lab test. So as a result, line codes can you can have multiple line codes for the same lab test of interest. For example, if you want patients who have a hemoglobin A1C greater than 7, there are over 10 line codes that represent variations of hemoglobin A1C. But from a clinical standpoint, it doesn't matter. All you need is patients who have a hemoglobin A1C in the record, no matter how that hemoglobin A1C was done. So that imposes a challenge. Another example where there's a mismatch between what a user needs, what needs to express, and how the codes are used in an electronic health record system. Now, is it enough to standardized terminologies? Quite often we hear people saying, oh, now that EHR systems are using ICD-10 or SNOMED codes to represent the patient's diagnosis on the record, we should be able to exchange information, right? We're all using the same terminology. And the answer is no, that's not enough. And we're going to show examples why. So here's an example of a patient with mild persistent asthma, and this is a SNOMED code for that. Let's say that system A uses this representation in their system. There's one field for the code and one field for mild persistent asthma. Perfect. I should be able to take this code, send to another hospital. They should be able to read that code and understand that this patient has mild persistent asthma. Turn out that the hospital next door uses a different representation. They have their information model has three slots, three fields. One for a main diagnosis, in this case asthma, which has a different code than mild persistent asthma because I'm just saying it's asthma. There's a qualifier, another SNOMED code that says persistent, and the severity is mild. So by combining these three codes, we get to the same concept, mild persistent asthma. But system A and B would not be able to interoperate and have semantic interoperability because there's a mismatch in the way they represent information, even though they're using the same standard terminology, which is SNOMED. Here's another example. One system represents a high serum potassium using a SNOMED code. That means raised serum potassium level. System B has a SNOMED code for the lab analyte, or it could have a line code that says serum potassium. It has a result of 6 and a unit of milligrams per deciliters, and the interpretation is high. So they are talking somewhat about the same thing. If all I need to know is give me all the patients who have high serum potassium, both systems would be able to answer that question, even though they're not interoperable. But this system has more information than the previous one. This one is saying that the result is actually 6, and this one is just saying the potassium is raised. So again, examples where systems are using the same terminologies, but they're not interoperable because they use different information models, and because this information model is less robust or has less expressivity than the one below. This one allows you to capture more detailed, granular information than the one above. So why is it so hard? I mean, we have been able to standardize things in information processing in all sorts of fields, and banking is usually the first example to come to mind. Would banks exist without being able to exchange information among themselves? You would probably not choose a bank that cannot transfer money to other banks. So in healthcare, we have a few problems. There are several problems that make it much more challenging. But in terms of information, the main challenges are because related to the fact that information in healthcare is primarily structured as text and not coded structured format like in banking. And in addition, we have problems such as negation. We have information that's ambiguous. We have things like patient may have this condition, or quite possibly the patient will respond to this medication. So there's a lot of ambiguity in the language uh, that we use to represent or to express healthcare and and to describe a patient. So the problem of nomenclature, for example, it's not that we haven't tried to solve this issue before, way before computers were available. This was recognized by William Farr as a problem that should have been solved. And over 100 years later, we're still trying to fix this problem. So let's look at an example of what quite often happens when we are trying to find patients that meet certain criteria. That's a very common kind of problem in healthcare informatics. You need to find patients who meet some sort of criteria. You can do that for quality measures. You can do for finding a patient cohort for research, or you can want to find patients that meet certain criteria to receive some sort of treatment. So let's say I have a task that I want to select all females, 65-year-old patients discharged with myocardial infarction. That should be easy, right? Well, here's one example. One EHR system might say, we got a 69-year-old female with diabetes, hypertension, and a previous MI, this patient presents with flu-like symptoms. So that patient does not match my criteria, even though I have myocardial infarction in the record. So first, myocardial infarction is abbreviated. So if I just searched for myocardial infarction, I wouldn't find this patient. Second, this is an old myocardial infarction. I don't want those patients. I want a patient who was discharged for a current myocardial infarction. And this patient was in the ER for flu and not for myocardial infarction. Again, I want the patients with myocardial infarction. Here's another example. The patient meets the criteria for age and gender. Patient has chest pain, and we got MI here. Let's say that I remember to search for both myocardial infarction and MI. But here we have a qualifier called ruled out. That means we're trying to see if this patient has MI, but at the end, maybe the patient was discharged with something else. So that patient would not meet our criteria. Here we have a slightly different option. This patient meets the age criterion, does not meet the gender criterion. He has MI on the record, but we're saying that we need to rule out. That means MI is our hypothesis. So maybe this patient meets our criteria, but we don't know yet because we're just saying we need to rule out MI. We need to wait to see what's going to be the final diagnosis. So it's quite challenging. That's a very simple query, and already we see the kinds of challenges that we would face. Another example, this is a granularity problem. The patient does not meet the age and gender criteria. In here, we have the patient was admitted, not discharged. Admitted. We want patients who were discharged. And but here we got anterior wall infarction. This is what I want to focus on the example. We don't see myocardial infarction here. Even if this information was coded, myocardial infarction would receive a code. Anterior wall infarction, which is more specific, would receive a different code. But anterior wall infarction is a kind of myocardial infarction, so that's good. That's the kind of patient I want. But the codes would not match. So here we have a granularity mismatch. We have in the query something more generic, more general than what's in the patient's record. So systems, an information system that would query this record, would submit this query, would need to be able to expand myocardial infarction to all the different kinds of myocardial infarction to be able to retrieve those patients. So here's a more computer friendly example. We got every piece of information in this query is stored in a structured format in different slots. Like in a spreadsheet, you would have different columns. I got a female is one slot, the age is another slot, the fact that the patient was discharged, so it's a discharge diagnosis, and the diagnosis is myocardial infarction. So uh, here we have a system which has age 78, so check off the age requirement. We got gender, female, check off the female requirement. Discharge diagnosis, acute myocardial infarction of inferior wall. We got a SNOMED code for this, but our system that's querying this knows that it needs to expand myocardial infarction to all the children codes, which include this one. So now I find this is a match for me. This other one matches the age, matches the gender. Wait a minute, we got past history of diabetes, hypertension, and MI, and the discharge diagnosis is pneumonia. So that won't work. But at least we have in this system the uh, old diagnoses are separate from the current discharge diagnosis. Okay, let's look again at the multiple granularities problem, because that's one of the most important challenges that people face when doing queries. And whenever you get into the data science space in healthcare, you will face multiple granularities. So here we go. I want patients who are currently on a beta blocker, or I want to check what percentage of post myocardial infarction patients are receiving a beta blocker. So that's much easier to say I want to see patients on a beta blocker, which is a drug class, than having to list all the hundreds of potential beta blockers available out there. Another example is for drug allergies. Rather than having to say all the different forms of atenolols, all the strengths or all the forms, I would just say patients allergic to atenolol in general, no matter what kind of atenolol. For a drug prescription, like we mentioned before, we need to provide the strength, the form, and the route. And finally, if we want to dispense, the pharmacy to be able to dispense that drug, the pharmacy dispenses a prescribed drug, but also with a quantity. So we have here bottles of 90, for example. And the pharmacy needs that same level of information to be able to bill for that drug. So again, we got multiple granularities. Quite often, one information system uses one level of granularity, but a user of the information may want to express their queries at a different level. So, concluding our lecture, the main implications for data science, folks who will work with data science applications, for research purposes, for quality measurement, for clinical decision support, will need to keep these things in mind. Number one, data will come from different sources. In nowadays environment, quite often you will have to pull data from, let's say, the billing system, the scheduling system, and the lab. And those are completely different sources, and they use different formats, different terminologies. Some of them are standard, some of them will not be standard. So you will have to address those issues before you even start working on your own applications. People quite often talk about mappings like they were a perfect solution. Mappings are rarely perfect, and we have mappings between terminologies, such as ICD-9 between ICD-10, or a walkthrough from SNOMED to ICD-10. You always lose information in mappings. They're never perfect. The same thing is true about information models. For example, EHR systems have their own proprietary information models. When an EHR system adopts a standard, they need to map their internal information models and terminologies to standard ones. There's always loss of information in that kind of mapping. So what happens is, if you receive a standard data in a standard format from one information system, it might not look the same as the same kind of data sent by a different system. So you have to keep that in mind. It's the kind of noise you will have to be able to deal with. We talked a lot about granularity and what happens when there's a mismatch. That's more the rule than the exception. So the structure of standard terminologies help deal with the granularity mismatch problem. But you have to keep in mind that just being able to say, I would like to query all my patients with myocardial infarction is not enough, because there will be a granularity mismatch between your query and the way data is represented in a clinical system or any kind of a healthcare database. Even though we have standards, as we've seen, there are many of them. And in healthcare, we have tons of standards that basically do the same thing or have overlaps. And so we got to be able to manage those multiple standards or multiple ways. Even within the same system that uses the same standard, you can have the same kind of information represented in different ways. And one example is family history. You may have one clinician who prefers to use the notes, the clinical notes, to write family history information in an unstructured way. Other clinicians may want to use a template, which is a little more structured. And yet another clinician might want to use a highly structured family history tool that stores information in a fully computable way. And this can happen in the same healthcare organization, in the same EHR system. So you have to look for that and not just rely on one source of information. Always look for multiple ways clinicians might be storing some kind of patient information in a patient's record. There's the notion of null flavors. So the lack of information or the absence of information in a patient's record doesn't mean that the patient does not have it. For example, if you find nothing about hyperlipidemia in a patient's record, you don't find a lab result, you don't find a mention of hyperlipidemia, it doesn't mean the patient does not have it. It just means that nobody documented it. Another example is the lack of field that's optional. It might be just that a clinician didn't complete that field or didn't enter information for that field, and therefore it's just absent. But we don't know, we cannot make any inference about the patient when we have those nulls. Um, Another problem is negation and ambiguity. You have to look for when you are processing um, information in free text, negation is and ambiguity are really important. So it's not enough to just look for terms in a note that say asthma or myocardial infarction. You need more sophisticated tools that are able to detect things like negation and ambiguity in the language.